Matthew Stover from Temple University. He's going to talk about profinite groups and complex geometry.
Great. Many thanks to the organizers for the invitation. Yeah, so I'll talk about a few things I've been doing in the last few years, I hope. So some more recent stuff that maybe you've heard me talk about before, but with Sam and Claudia Eisenrich and PRP and Stefano Vidusi, and hopefully I want to get to some stuff I did with Timmy at Toledo that's actually a little older, but I want to sort of maybe focus in there on some profinite questions that have not been answered. But so, segueing from the last talk, we've just left this on the board. So we'll start here. So sort of plan of the talk is I'll start by talking about sort of one-dimensional in the complex sense, Riemann surfaces, and then maybe talk about some higher dimensional stuff where things get maybe a little more interesting, or a little less rigid, maybe. Right. So for now, to start, the X will be a compact Kähler manifold. And if you don't know the precise definitions, it's really not going to matter. The point is, this is a class of manifolds where you can attack problems using tools from complex geometry and geometric group theory. That's somehow what we're going to be after. So here's theorem A. So if pi1 x is residually finite, and its profinite completion is the profinite completion of a product R genus each greater than or equal to 2, then this is in fact an isomorphism. Okay. These groups are profinitely rigid amongst Kähler groups. And this is just a well-studied class of groups. These are the fundamental groups of compact Kähler manifolds. The first thing I'd like to maybe bring up is that our theorem is virtually false. And so this is due to our Catanese Fritz Grunewald. So you can have a product of two Riemann surfaces with free actions of finite groups. Y2. So these are sometimes called isogynous to a product. So just like flat manifolds that aren't tori. These groups not isomorphic. They do have the same profinite completions. And the point here is, this goes back to Sayre, is that these y1 and y2 are smooth projective surfaces. And they can be defined with sort of algebraic coefficients and equivalent under the absolute Galois group. Okay, so these are cut out in some projective spaces by some polynomials that have algebraic coefficients, and you can hit them. You can hit those polynomials with the absolute Galois group, and you change 1 to y2. And Sayre's observation is that this doesn't change the profinite equation.
S1 and S2 are just surfaces, two-dimensional surfaces.
Mm-hmm. Yep. Yep. Just Riemann surfaces. Yeah. So the quotients won't be a product; they're just covered by a product.
It will be what?
Yeah. So so these will be, you can almost write this down very explicitly. These will be Riemann surfaces, and you'll have two actions of a finite group on the same product.
The finite groups are the same order?
They're the same group, in fact.
Same group, so
It's the same group. You don't have to assume that.
and Y1 and Y2 should have the same genus.
Well, they don't have a genus because they're not products themselves. They're just covered by products. The action here isn't factor-wise. In fact, you just need to act freely on one factor and act with fixed points on the other factor. So they're still manifolds. The action on the product is free, but on individual factors it's not. It's not a product action.
It's a final product.
Yeah, exactly. Yeah.
Can you get F1 and F2 of different orders? Or is
No.
there some reason?
No, and so a corollary to theorem A is if you have X compact Kähler and pi1 X profinite completion is isomorphic. Pi1 of Y profinite completion for Y, let's say even an arbitrary product of higher genus surfaces, modulo some finite group acting freely on the product, then X is also, if you want to worry about, I'll be sort of pedantic about complex structures. So there may be different complex structures here. So that you could make these actions holomorphic if you don't care, just take the same surfaces. But the same group, right? Because this will have a characteristic subgroup. You hit it with the theorem. And then this will have a cover. This is associated with that subgroup. And it'll have the same profinite completion. You hit it with the theorem. And then the bijection of finite index subgroups from profinite isomorphisms respects index. And so the F has to have the same order. In fact, it has to be the same group because you just used a matching of profinite completions to do it. Yep. Okay. So in a sense, the theorem is virtually false, but in a very, very controlled way. Okay. So they produce these very interesting examples in this paper, and that's all you can do. The question we can't answer is whether everything has to strictly come from their construction. So it'd be interesting to know whether you could do a construction like this where it doesn't actually come from using the absolute Galois group to twist them. Okay? So, great.
The SI primes can be different from the SI.
Yeah, so here I'm only being pedantic about the complex structure. So these are homeo to the SIs. If you can do this all in the sort of working with holomorphic actions. You always know for some finite group action there's some complex structure for which it acts holomorphically and blah, blah, blah. So yeah, the prime is just to keep track of complex structures. Oh, and an addendum. The theorem A is that if this X is aspherical, it's not, then it's actually homeomorphic to a product of surfaces. Right. And I'm not saying anything other than you have two aspherical manifolds of the same fundamental group. They're going to have the same cohomological dimension, blah, 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 blah. I mean, so I'm not saying anything new here. All right. Yeah, so really the corollary, you can say we even get some sort of finiteness. The profinite genus for Kähler manifolds. Isogenous. To a product among all Kähler manifolds.
It's not trivial, right? You need to Borel conjecture.
Oh yeah. That's right. Yeah. I mean, that's old hat now. But yes.
You need to say aspherical somewhere.
I did.
On the last thing you wrote, you should say aspherical.
Oh wait. You mean for this
Yeah,
one?
that, and then the next
Yeah.
next column.
Yeah. Sorry, this is the aspherical board.
Yeah.
I guess in this case, yeah, if you drop the aspherical condition, you'll still get the isomorphism of fundamental groups, not the homeomorphism. Okay. So if G, you can add abelian factors to this. So you know, the keen of you in the audience are probably wondering, what about tori? We can just. I'm going to sort of to keep this relatively simple. And in fact, or co-compact Fuchsian groups. Could throw those in as well. I'm just trying to not make this too complicated. Actually, sorry, I'm going to restate this. I'll state this slightly differently. I do want to remove the hats. Let G just be that product. This would be a little cleaner. G. Yes. Profinitely rigid. And growth rigid. Amongst individually finite Kähler groups. Okay, so for this talk, I'm going to ignore the abelian factors. They're a bit of an annoyance, but I'll sort of, I'm going to ignore growth and deep rigidity as well, but I'll sort of mention what one needs to do here. So to add this case, you need to add a little bit from, so this takes in ideas. From Milton and Zaleski things that they did for Seifert fiber spaces and their profinite rigidity. So go look at the paper or just whisper to Sandra in the talk if you care about this. if you want to talk about growth leak rigidity, one thing you'll care about is, well, you should care about this anyways, because it's a great theorem, but a theorem of Bryson and Wilton about finitely presented subgroups of direct products of surface groups and abelian groups. And essentially, I'll just say it out loud for those that care. The point is you have some enemy group inside, it's then separable, because it's the fundamental group of a compact Kähler manifold. So it's finally presented, so it's separable. So then the map on profinite completions is an isomorphism, but then this map then becomes an isomorphism. Yeah, so you need to know that finitely presented subgroups of these groups are separable. Okay. So what is the engine for all of this? The engine is something called the universal homomorphism. So let gamma be our fundamental group. Then there exists Fuchsian groups. Delta 1 to delta r, and homomorphism rho some components in this group, the direct product, so that we have two properties. Well, it has several properties, but I'll only mention a couple. These kernels are finally generated. Maybe the individual row i's are onto. The finally generated kernel. You have, say, a sigma from our gamma onto a Fuchsian group, Koch-Back Fuchsian. Then sigma factors through some row I and has finally generated kernel. If and only if sigma is one of the row i's, up to obvious like automorphisms and things like this, right? You could conjugate down in the target, things like that. Okay. So I hope the word universal seems reasonable in this, but so maybe I should attribute this as well. So this and Claudio really sort of did some work putting this in the right language in this sense. Okay. So any questions about that? So the point is that given a compact Kähler manifold, you have this sort of homomorphism to a product of Fuchsian groups that determines all homomorphisms to Fuchsian groups. And I'll factor through that. Okay. And the sort of magic thing is that these are precisely the homomorphisms with finitely generated kernels. And there's a sort of geometric idea behind this. Which is that these finitely generated kernel is really telling you that these are coming from fibrations of X over hyperbolic two orbitals. Right. And so these are precisely coming maybe from, well, won't go any further than that. so the image of the sort of general fiber, these can be singular fibrations. These are sort of singular in the fibrations in the complex sense. So they're allowed to have singularities, but then there's a general fiber, which will be some compact manifold. So that's how you see finite generation of the kernel, because the kernel of that homomorphism will be the image, at least, of a homomorphism of a general fiber, smooth fiber. Okay? And the point is that this is actually a bijection. For the theorem. Okay, so this is the sort of engine that's going to get us going to talk about the other results. Theorem C is if let's call them the G, H, or Taylor groups. And we have isomorphism of profinite completions, then G and H have the same universal homomorphisms. Right? And so what does that mean? So if we have maybe rho 1 to rho r, for G and sigma 1 to sigma s. For H, then R equals S, and up to the obvious things you need to take care of, we have that on profinite completions, which way is this going to go? Sigma I is going to go first. Okay. These are the induced. So you need to be a little careful here. You're not going to.
Something confusing here, but now I think it's the confusion because of the definition. What do you say that the new this is tau, whatever it is, from gamma to sigma, the co-compact, then it factors through some rho I.
Yeah.
And the kerr is finitely generated, then it must be the same.
Yeah. So these are precisely. So these are homomorphisms. These are precisely the ones.
This is trivial because if it factored through some of the rho I, then the kernel of it is a pre-image.
Yeah. That's right.
So no normal subgroup of surface group is finitely generated.
That's right.
Then
You do. You proved it. You got it.
So it's not part of the definition.
No, this is a list of properties. Yeah.
This is kind of a
Yeah,
list of properties.
Yeah.
So what universally?
It's universal for homomorphisms to Fuchsian groups.
What?
For surjective homomorphisms to Fuchsian groups.
No, but you said that it factored through some of the rho I.
That's right.
And this is a max, like rho 1 up to rho r is a maximal possible such.
Yep.
So there is something non-trivial.
I think in your third start, if you start the sentence with for all.
Oh. There you go.
What? To every map, okay.
So every homomorphism from gamma to a Fuchsian group is a homomorphism from this direct product.
So every homomorphism to some co-compact lattice should factor some of that, and if the kernel.
Yeah. So this as you're indicating, this is the part. This is the part.
Finitely general, then it must be equal to.
This is a remark, and you proved it. Yes. Yeah. So this is the part with content.
Okay.
And the Fuchsian groups of the homomorphisms, otherwise you
Yeah, that's right. So this is up to any automorphism of the base, and this is why. And I'm glad you mentioned this. This came back to what I was about to start muttering. Is in this case, I'm saying that the induced maps on profinite completions come via the isomorphism of profinite completions, right? But you could then hit these profinite surface groups with automorphisms. These things have absolutely enormous automorphism groups. Yeah. It's even relevant here.
But wait a second, is it rely? I mean, is it rely up to?
Yeah, up to all the obvious equivalences that would make it wrong. Yeah, that's right. So the one thing I would like to point out here, so people have rightfully seen some assumptions that maybe I leave out here and there. Here is no residual finiteness assumption. Okay? I didn't omit it accidentally. Yeah.
So in this engine, X is closed?
Yes, it's always a compact manifold. Yeah. There's almost certainly a quasi-projective version of this that involves free groups and blah blah blah. Yeah. No, I think this is I would rate that as something where we just need to check some details and then.
And you have to allow non-compact function, and you have.
Yeah. But this theory is developed. There's also a sort of connection to the BNS invariant that one needs to prove all of these things. So you need analogs in the sort of quasi-projective setting for all of these things, but then it goes through. I mean, wait till we've written it up, but it should be okay. And yeah, so I'll just say it as a conjecture with some confidence. We could prove profinite rigidity of free groups among fundamental groups of quasi-projective manifolds, which is a much broader class of groups than Kähler groups. With a fair wind coming to an archive near you someday. We'll see. Okay. Oh, and notice yellow is for. So we do not give a reproof of this. We apply it. Bryson. Condor. Reed. So we actually need to know that Fuchsian groups are distinguished by their profinite completions. That's an element of our proof. At the end game, we apply that theorem to get the matching. Okay. So we prove that you get the same list of profinite completions, and then we smash it with theirs to make sure it's the same actual Fuchsian groups. Great. That's fantastic. That took way longer than I thought. So just an aside for those that care, they'll put it down here where nobody can see it. So if you care. We also match BNS invariants. So there exists a linear isomorphism on the rational first cohomology. So that when you tensor with R, BNS invariant for G. BNS invariant for G. Okay, I'm not going to go into that, but all right. Move back over here. All right, so I want to sketch some elements out for this. Theorem C. every fact I'm about to write down has come up in some aspect already this week. In fact, much of it this afternoon. So to start, we'll have gamma will just be finally presented. I'll assume it's residually finite for now. Just for some pieces. Pick lambda will be inside the profinite completion a dense subgroup. So L, M, and O, L comes first. We have the first L2 Betty number, this lambda is greater than or equal to first L2 Betty number, gamma. So on the level of Betty numbers, I think everybody in this room is profinitely able enough, but we also get an inequality on L2 Betty numbers. Fuchsian group, then its profinite completion has no finite normal subgroup. This came up in the last talk. We have that if first L2 Betty number is non-zero, then finitely generated normal subgroups are finite or finite index. The last one. So if we have a normal subgroup of this lambda, then it's in fact normal in the profinite completion. I think this maybe even came up. I'm not sure if this one did. But this is a fun exercise. Okay. So if you stop caring about Kähler groups, then should I prove this? Okay. So, so this is the sort of elements I'm going to try to put together here to sketch this out. All right, so we have this universal homomorphism.
I don't think you wrote what you meant. What do you mean to write?
Oh, and yeah.
And closure?
Well, oh, finite. Yeah, sorry, and's a finite normal subgroup. Yeah. Okay, now now it's gone from wrong to exercise. You know, lambda looks just like n when you're this close to finite particle. All right. So this product of surface groups. Delta I. And so we'll have profinite completions. And let's suppose that we have, let's see, I need a group name, so G, and, well, I'll just say it this way. I want hat, so let's call it C hat, some Fuchsian group. Right. So then let's call iota the inclusion map. Any other notation I won't? I think I'm good. This is a subjective homomorphism. So is that this map, so get this in the right order. Some rho I. Okay? So it's a profinite version of this universality. Right? So maybe look at the case. So profinite or Fuchsian group, right? We need to deal with an arbitrary Fuchsian group, but let's just consider the case where the abelianization of this is infinite. Okay, and now you just need to find a good for the general case. So you need to pass to a cover cleverly. Talk about the arbitrary case, but so the point is now we're going to put all these ingredients together. So that lambda be the image group. Living inside this profinite surface group, but now we get that the first L2 Betty number of lambda is greater than 0. Okay. And in fact, the first Betty number is greater than 0 as well. And so now just fix, so just sticking with this image group, so now fix some homomorphism onto Z. And you conclude, using precisely all of that the kernel of this is not finally generated. Okay? But then, as in the proof that that additional hypothesis on the finally generated kernels in the universal homomorphism, you see here that the kernel of the induced map is not finally generated either. And then it's a theorem. In the way we're using it, Napier-Ramachandran. There exists a holomorphic map from X. C is the compact. Not surface. Genus. At least 2 inducing. Oh, maybe I should use hat. Maybe I was too. I mean, they all look the same. My terrible handwriting. Okay, so out of all of these facts, we get a kernel, a homomorphism onto Z that's not finally generated, so it induces one. But then there's a theorem in Kähler geometry that says there's actually a map to a Riemann surface. So any homomorphism onto Z with infinitely generated kernel comes from, you map it to a Riemann surface and then map that to Z, and well, that kernel's not finally generated, so that one's not either. So then, but now we get a pi1 trajective homomorphism, and so you can dial all this backwards. I guess you just go that way, and you see that this sub rho I, and in fact, you could look at a diagram going to this this lambda, and then you push the kernels around with the same ideas. And you see that you know, when the kernel is finally generated, is a rho I, etc. So we get uniqueness. So in particular, we get all of what I'm really trying to say here is that we get a profinite universal homomorphism. And so now, you know, if you have, so then you get compositions to these factors. Let's say H has sigma 1 up to sigma r for H. Product of sigma i's. So then, now you just chase around the diagram. Well, use theta. And theta inverse plus uniqueness. And you get the for G, sigma I for H, we get this isomorphism. Right. Like I was saying, you chase this around and you get isomorphisms of profinite completions of the surface groups. And then you apply Breinson-Condor and Reed to get isomorphisms of Fuchsian groups on the nodes. All right.
Great, so you didn't know that rho is injective, right? You know,
That's right.
Right.
Yeah. So now if you assume it's residually finite, then assume it has the same profinite completion, then it actually injects into that product of profinite Fuchsian groups. And it's a finitely presented subgroup now, and it's separable, and so you get this isomorphism, but then they must be isomorphic. So yeah, basically once you have the correct homomorphism, now if you assume it's residually finite and has the same profinite completion, then it injects inside, and now you're just playing sort of well-known games to get the isomorphism.
So there are examples where rho is not injective. of like
Oh, yes. Yeah. I mean, okay, I can cheat. So that there are examples through Domingo Toledo of Kähler groups that are not residually finite. Those groups have property T. So that doesn't, they have no homomorphisms to Fuchsian groups. Yeah, actually what I wanted to end with in the last 15 minutes were sort of questions in that direction. So let me go there. So right, so somehow we've been thinking about Riemann surfaces, products thereof, but so what are the Gromov? Hyperbolic. Kähler groups, okay, so we love higher genus surface groups. And here actually very little is known. All right, so there's a unit ball in Cn with ergo metric. And so locally symmetric spaces. All right, so this has been known for a long time. This somehow goes back to Picard even, and there's lots of examples, arithmetic groups, and there are many mysteries. And so you could ask, what class of Kähler groups don't come from this? And there are very, very few from there. So there's work of Moscow and Su and Zhang, so this is around 1980, for dimension 2, so complex dimension. This was more n equals 2, Dero gave some examples, n equals 3, and then with Domingo Toledo, yes. And greater than or equal to, there exists examples not homotopy equivalent to locally symmetric. So our knowledge of negatively curved Kähler groups is actually quite poor. And so, okay, we want to start maybe talking about profinite properties of these profinite rigidities. So, so Serre-like ideas you can produce lattices in 2, 1, 1 for all n greater than or equal to 2, so 1. You can make it arbitrarily long. So these are not isomorphic. They have the same profinite completions. Just leave that. My favorite examples, they're fake. Fake projective planes, x1 and x2. So this just means that the complex cohomology is isomorphic to that of P2, CP2. So x1 is not homotopy equivalent to x2, but the fundamental groups have the same profinite completion. In fact, and the thing I liked about these, you can find examples And there should be some more sort of interesting mileage out of this, I think, but I can never quite get there. You can actually find these in sort of diamond, where this is a Z-mod 3 squared quotient. And in fact, this lambda can be written as semi-direct product with some torsion element. So you can find these examples. Okay, so profinite rigidity is out. But there's some remarkably simple things that I don't know how to do. Let's see. Where do I want to start? So maybe, first of all, you could take one of these lattices. So these things have lots of H2. Even over Z. These can have. So you can get lots of Z central extensions. And if you really care, you can ask me later. So, but, Domingo and I proved that certain of these have these extensions always what I'll call very residually finite. Now, I think very residually finite has been defined in a bunch of papers, but here, I mean, even all reductions mod n. Are residually finite. Right, so if I just knew residual finiteness for this, this central extension, I get some infinite list of n's for which the reduction mod n is residually finite, but we actually get all of them, and the point is we construct a two-step nilpotent quotient. That's 1-to-1 on the center. And then nilpotent groups are residually finite enough to get all the reductions mod n as well. What I'd really like to know, and can't answer at the moment, is are co-compact good groups. So I have a bunch of applications of this, if you can prove goodness. But I don't know, and maybe, so what Domingo and I sort of toward, I would even have applications if it was too good, so it's just fun when you say it. So I just want isomorphisms at the level of second cohomology. somehow the importance of second cohomology in complex geometry makes this a very interesting question. The point is that sort of what we do here is so the strategy we take is we show, so you have this element in the second cohomology, we show can pass to a finite index subgroup. So that the restriction of this lives in the image of the cut product. Image. Cut product. Primes. And what that's saying is actually these are pullbacks from a torus, from a map to a torus. So there's a map just from right, so I'm thinking about my space, mapping to some torus. So this class is in the pullback in alpha star. Right, but then, so that means that this phi is a pullback from let's maybe just say CVM Z by goodness. So anyways, I think that there's some hope that one might be able to use the techniques that Domingo and I use, at least in this case. There's some more sort of cut product techniques to go for higher degrees. But so, you know, this is not an indication, I'm not maybe conjecturing these are good, but there's maybe some sort of modicum of evidence that these may be.
Too good implies that every extension is residually finite.
Yes. Yeah.
Is it equivalent?
Yes. Every extension by a finitely generated residually finite group being residually finite is equivalent to being
Basically, even by finite, it's the same.
Yeah, that's right. Okay, so I have 1 minute left. I have several more questions, but I kind of like that one. I think that one, maybe some people in this crowd may have ideas and may solve it, so maybe I'll let you go so you can go solve it. Anyways, thank you very much for your attention.
Questions?
Yeah, I need to ask, your profinitely isomorphic lattices,
Yeah.
which are not isomorphic in QA, do you know if they have the same volume?
Yes.
That
Yes.
comes out of the construction directly.
Yeah, it comes directly from the construction, and yeah, the point is that you want to prove that they're so. In this case, it's just sort of by definition because they both have the same Euler characteristic by having the same Betty numbers as the complex regenerative plane. But yeah, this one comes from, essentially the point here is you do the exact same thing you do in higher rank. You make sure that the arithmetic groups locally match up everywhere, so you'll get the same volume because you're in the same group, so you don't even have to worry about local factors. And then and the point is you prove that these solve a moduli problem. So as sort of Shimura varieties, they're Q bar over Q conjugate. And so you know, if it had the congruent subgroup property, I would have been done, but I don't have that. So then you use this extra Shimura variety technology to get the profinite isomorphism. So turn that crank. But yeah, so then it follows straight out at the same volume. Yeah, Martin.
So if you stick to the Kähler setting, can you prove that you're profinite equivalent to hyperbolic guy then you're hyperbolic?
No. No. I actually can't even prove that. This is sort of not the same question, but I can't even prove that the examples Domingo and I constructed are residually finite. Like all of these, like Mastasu examples and all these, like we don't even know if they're residually finite. Their profinite completions are a total mystery to me. It could almost be the profinite completion of the lattice we used to build it with a branch cover construction. I doubt it, but yeah, the ignorance is extremely high.
So is there any reason to focus on Kähler ones instead of more general complex?
Only in the sense that you get slightly stronger tools from complex analysis, like these fibration theorems. I mean, so for instance, every group is the fundamental group of a singular complex projective threefold. So so if you allow like singularities in the complex manifolds, then it's totally gone. Because every group can appear. Now you would just, I mean, if you could go and use complex geometry techniques to prove profinite rigidity of surface groups, then great. But yeah, the point is it's sort of very volatile where you weaken enough assumptions that all groups become fundamental groups, and so now you're probably in deep trouble.
More questions? No, it's thanks for your hand.